Welcome to the Newton tutorial series. I'm Mike Cruz with AC-Tek, and in this tutorial I'm going to cover some of the advanced features that you might use when you're generating material in Newton. So in the last tutorial we covered just basic generation and how to evenly distribute your layers so that you'll get a steady stream of material on the belt. But now we're going to cover some of these advanced properties that you could play with. So I've opened up that same cylinder that we were looking at the end of the last tutorial. I re-imported the cylinder and doubled it in size. So when I look at a top view here, if I've got a 2-meter diameter circle now, it's not covering that entire space of the cylinder. So if I set my generation time to say 5 and let's set this minimum particle gap to 75 and generate my material. Alright, 24 layers and whatever our minimum layer separation is okay. Now if I go ahead and run this, obviously we generate these layers. Nothing special. I actually want to decrease that tonnage. Let's make it 300. But what if we wanted to give this material an initial velocity? Maybe I want to throw all this material into the corner here. So I could say, well, let's give it an initial velocity of 1 by 1. So now all this material is going to start out moving in this direction with 1, 1, 0 velocity. If I regenerate, and say solver run, go to a top view, you can see we're generating these layers, throwing them into that corner. So what about the z velocity? Well, we have to be careful because obviously we can only generate these layers as fast as we allow the layers to leave the generation zone. Because that, again, that minimum particle gap that we're looking at, we want that to be as close to 0 as possible. But if we say give it all a positive z velocity of, let's say, 3 meters per second, well, now I already have overlap. Okay, let's just say 2 meters per second. Alright, that'll work. So if I go ahead and run this, obviously we're throwing each of these layers up. And what's even the point of doing? There's no reason to give it a positive z velocity. All it does is waste time and force our layers to be spaced out more. But if we wanted, we could give it a negative velocity. Well, let's go back to 0 and look at our spacing. 1.87. So that's how much space we have. If I even give it a modest velocity of negative 1/2, we've already increased that minimum layer separation. So if I was trying to use a really high tonnage, let's say I wanted to generate a really high tonnage, like 5,000 tons per hour. We've got overlap here. But if I was to shoot all the material downward at a high velocity, well, now I can fit it all in there because this material is just going to generate and shoot right out of that generation zone, and it's going to leave enough space to quickly generate the subsequent layers. Obviously, my initial particle velocity is pretty high, so this material, as it hits the bottom, it's going over 10 meters per second. So you have to be careful not to set that initial velocity too high. But even a value between -0, a value between 0 and -1 is going to give you that biggest impact. It's going to give you a really big impact if you wanted to increase the tonnage there. So in addition to the x, y, and z initial velocities, we could also give it random velocities in the x, y, and z directions. So if I wanted, I could say, well, I want to give it some random velocity between -1/2 and 1/2 in the x, and -1/2 and 1/2 in the y. So for each of these particles, it's going to start out with a random x and y velocity. So I look at a top view, and if we can go there, you see they're each moving randomly as we generate them, which just creates an additional component of variability. But the z velocity obviously is still constant because we didn't modify that. I'm going to go ahead and turn this down to 0.005. 0.005. And I'm going to turn that down to 0.1 so we can watch this a little bit smoother. So what if I wanted to also give it a z velocity? Well, again, we want the max to stay at 0. We don't ever want to give it a positive z velocity, but maybe I want to vary it from -1 to 0. Now if I go ahead and run, oops, surface is transparent, Now you can see that in addition to having the x and y velocity, these layers are dropping at different heights now, or different rates, because we're giving it that random z component. So this material is just distributing itself much more randomly than if we just dropped straight straight layers with no initial velocity. And these random velocities are added to your initial velocity. So I could say, well, for sure I want all of my materials to have at least negative 0.5. And then these velocities would be added to that. Certainly, I could even bypass that. I say, well, that if I want it to be negative 0.5 and then up to an additional negative 1, I can just simply say, well, random max is negative 0.5 and random min is negative 1.5. That would be exactly the same as saying my initial is 1 and then this goes between negative 1/2 and 0. It's the same thing. Additionally, I could give my particles a random rotation. Let's rotate around the vertical axis. So now each of these particles is going to have a random rotation between 0 and 360 degrees per second about the vertical axis. So if I generate, and go ahead and run, those particles are all rotating. Some of them are rotating more slowly than others, but they all have that initial random velocity, or random rotation rather. And we can say, well, let's say 360, 360, 360, and generate and run. Now these are all going in totally random orientations. Just gives us yet another component of variability for our simulation. And obviously, you could have every one of these boxes have a value in it. You know, you would take the release velocity, you would add the random velocity, you would add the random rotation, and that allows you to completely control that initial velocity profile. So, other than those initial properties, let's now go down and take a look at our distribution. I'm going to open up just a new file and recreate our belt that we were working with in the last simulation, in the last tutorial rather. So say our same 40 to 100, bulk density 830, 1000. And let's just do one layer again on belt 1. So minimum particle gap, we'll say 10. Delete the bounding box gap. Alright, that's what we're looking at. Standard layer. But if I wanted, I could vary the spacing between these particles. If I say linear x, then what it does is it says, well, I have to enter a gap factor here. So if I enter 100 here, what it means is that from the left side of this box to the right, from the where's my origin? From the negative most x position to the positive most x position, it's going to vary this particle gap between whatever my minimum is and whatever this one is, because this is my x component. So it's going to vary between 10 millimeters on this side and 100 on that side, just like that. If I wanted to say 0 to 75. We got a 0 gap over here, and then it varies linearly up to 75. Or I could do that in the y direction. But you have to be careful because, well, you say, well, where's my gap? And this is because this is our x coordinate. So I could just delete that, but I got to put it in the y because now we're looking in the y direction. So now we'll be going from 0 to 75 in the y direction. Just like that. So when would you use something like this? Well, maybe we're trying to simulate the discharge under a vibrating screen or under a set of grizzly bars, and we know that there's going to be more material falling at the start of the vibrating screen than at the end. So I could generate material in this linear pattern and vary it, you know, all the way between, you know, as close together as I want and as far apart as I want. So in addition, we could also do a linear XY, which basically will vary it both in the x and the y direction. But right now this is set at 0, so when I regenerate it's going to look identical to what it just did. Oh, maybe it doesn't. It must want you to have both these gap factors defined, or else it won't do anything. So if I say 75 and 75, we're varying from 0 to 75 and from 0 to 75. I could set my minimum gap at 10. I could say we only want to vary in the x direction, we want to vary up to 50, but in the y direction we want to vary to 150. So now as we go this way, our size over here is only 50. But as we go this way, our size varies up to 150. And then, of course, we have the xy squared, which is just a quadratic distribution. And that one's a little bit more complicated. I think we only use that for one specific project. But it's a little bit more tough to use. So generally, you're rarely going to use anything other than a uniform distribution, or possibly a linear y distribution if you were using like a vibrating screen or a linear x. These other two, I don't think I've even ever used them, but they are there because we had added them for a couple specific projects, or a couple specific users had requested them. So we'll switch that back to uniform, regenerate. So now down at the bottom, here's just some other optional random parameters that you might use. This first one right here, mirror layers. So if you've noticed, this whole time we've been generating material, it always starts out smoothly on one side, and then it ends kind of, uneven on the opposite side. And that's because when we generate a layer, we start at this negative most x position. We basically start down in this corner, and we say, well, let's go up along the wall here, and now let's move over a little bit and go again, and now let's move over a bit and go again. So what happens is we get to this very last row, and we're starting to put particles in, and then we move over a little bit, and the first time where we see, oh, I can no longer fit a cluster here because I'm hitting this wall. The first time we do that, we force ourselves to start a new layer. So what happens is this is almost kind of unfinished, because what we see is maybe my next particle I wanted to generate right here was this teal 8 cluster right there. Maybe I wanted to try and stick that cluster right here, but I couldn't fit it. So what happens is Newton looks at our particle library and it says, well, this 8 cluster, I need to have 217 of them per 10,000. And according to my random generation that I'm generating, according to my distribution, the next cluster has to be that teal 8 cluster, but I cannot fit it. So we say, well, we force ourselves to stop and go to the next layer. And that's why the edge of this is kind of uneven. So obviously there's a very slight, the material is very slightly heavier weighted on this side than on this side. So by mirroring the layers, what we're saying is, well, if we generate more than one layer, we're just going to flip this so that we'll start at this side, and then the next layer will start on that side, and then the next layer will start on this side. So if I scroll through the layers, you can see that layer 2, now that side is smooth and this side is uneven, and layer 3, and layer 4. So that just allows us to keep our material equally weighted on both sides of this drop zone. So you could turn that off if you want, but there's not really any reason to. The increment multiplier. What this does is it allows you to speed up your particle generation. So by default, like I mentioned at the start, towards the beginning of the last video, Newton will try to, if I just generate one of these, Newton will try to pack these particles as close together as possible. And the way it does that is it defines this, it breaks up this entire drop zone into a very, very small grid, and it steps incrementally a little bit at a time along the x direction and along the y direction. But sometimes, for instance, if you have a particle set with a lot of big lumps, it can't fit those lumps very easily, and so it moves very, very, very slowly as it's trying to find a spot for this huge lump. And all it does is waste time, and you could end up with generation times that take way too long. So what this increment multiplier does is it says, well, the amount that we step in the x direction and then step in the y direction, let's go ahead and scale that. So by default, if this is blank, it's left at its default value of 1. So we let Newton decide what that increment should be. But if I wanted to increase it, I could increase it by a factor of 5. And what that does is basically now it's stepping 5 times as far each time it moves to the right. If I set this value less than 1, say 0.5, now it's stepping even closer than it normally would. So you can tell if I have my minimum particle gap right here, it's set to 0. But when I generated this material, there's clearly gaps. There's not exactly 0 space. And that's because of that finite grid. But if I set this to 0.1, see, it's taken way longer to generate this layer. But now these particles are even closer together than they were. If I said 0.01, now that's going to take about 10 times as long to generate just this single layer. Look at that, that's as far as it got in that 5 seconds. So you generally never need to set that smaller than 1, but if you want to increase the speed, so let's leave that at default and say let's generate 60 seconds of material. How long does it take? Well, we're going at a pretty good rate. Done. But if I said 5, done. It went about 5 times as fast. The point is that the only problem now is my spacing is no longer even close to 0. Before it was pretty close to 0. So if I just generate one layer again, so here's my one layer, and there's at least a 2 or 3 or 4 or 5 millimeter gap. But if I reset that back to 1, it's much closer together. So there's a trade-off between, if my material generation is taking 5 minutes, and right now I don't necessarily need the clusters to be super packed. Right now I just need to generate some material so that I can test out some of the parameters of my simulation. So I could artificially inflate this to, say, 10, and that's going to speed up so I could generate my whole 60 seconds of material in just a fraction of the time. And obviously there is an upper limit to what this could be. If I said this is 100, well, now we're so high that we're getting some overlap. And what you can see is basically it's turning it into kind of a square distribution, because now we're stepping about this much. Each time we shift over, we're moving that far, and that's completely unrealistic. So, maybe what if we do 50, or if we do 40? Oh, clearly there's a small issue there with that grid size. I think what's happening here is the center position for these clusters happens to be exactly overlapping. So then there must be a small error that we should investigate and correct. But generally, you don't want to set this increment layer any higher than about 10, because then that's going to allow us to generate material about 10 times faster. But the real advantage to this is when you have big lumps. If you generate something you have some fines, but you also have some huge lumps, you can use this, and you can set this to 10 or 20 or 30, and it'll generate those lumps much faster. And even by default, looking at our regular generation, what do we see when it's finished here? 140 layers. So to get this 1,000 tons per hour for 1 minute, it took 140 layers. If I increase that to, say, 3, it's going to generate about 3 times faster. But now it's 151 layers. So now, because of this extra space, it took an extra 11 layers to generate that, to drop that same amount of material. So my minimum layer separation has gone down. Now it's 0.682. If I increase that to, say, 10, well, now we have 176, up from 140. Our minimum layer separations dropped from 0.67 or whatever it was down to 0.47. So this is kind of almost another way that we can modify the minimum particle gap, but really the only time you need to modify this is if you're having really long generation times. But even just for any particle set, if you go in and just stick a 3 right there, you'll get faster generation, but still the distribution is still almost exactly what it was when you leave it at the value of 1. So it's just a speed up factor is all it is. Alright, next, particle count. Basically, when we generate this material, if I'm generating 60 seconds of material, you can see right here, we're generating 10,000 random clusters for material set 1. Done. But actually, we actually generated 111,000 clusters. So you say, well, how come it took that long to generate the first 10,000, and then the other 100,000 generated in an instant? And that's because what Newton does is it only generates, by default, it only generates 10,000 clusters randomly. It takes those clusters directly from this clusters per 10,000. But after it generates that first 10,000, then it says, okay, now let's just go and copy the layers that we already have. So if I look at this very closely, and I see how many layers do I get? 1, 2, 3, 4, 5, 10. There were 13. I believe there was either 12 or 13 layers. And that means that even though I have however many layers I have, I only have 13 unique layers. So this has 816. If I go back to layer 1, that had 814. So now if I look at layer 14, let's compare this layer 1, 814 clusters, and this one in the corner is this yellow 8 cluster. Now if I go to layer 14, boom, 814 clusters, and it's that same yellow cluster. So this is identical to layer 1. So that means that we are generating only 14 layers, and then we're just dropping those over and over again. And usually 14 layers at 5.5 seconds, usually that's enough time that we have a good random distribution of material. But if you want, you could say, nope, I want you to generate 100,000 particles before you start copying layers. Then as I generate, now this is going to take much, much longer, because now you can see generated 100,000 random clusters. So then it'll get to the end of that, and it'll only generate an additional 10,000 clusters. It'll copy those. It'll start over and copy them. Alternatively, if you were generating a really, really coarse particle set, and maybe you say that 10,000 is too many, we only need 1,000. So then we say, oh, it only generated how many unique layers now? Only 2 unique layers, because there's our 4 cluster. Layer 2 is different. Layer 3, we're back to the same one. Layer 4, layer 5. So you look at that and say, well, that's probably not enough variability. But the default value of 10,000 is usually sufficient, but you can change that there if you want. Quick gen mode. This is kind of similar to our increment multiplier. What quick generation mode does is it says, well, let's take my drop zone and let's divide it up into a grid size that is equal to whatever my maximum cluster is. And let's just go through that large grid and stick 1 cluster in the center of each spot. So the grid size is going to be about as big as this cluster right here. So if I do that, it generates really fast, but you can see, we're not trying to pack these clusters close together anymore. So if I look at this, this requires 224 layers. If I go back to our advanced complicated generation mode, it takes a little longer to generate, but clearly it's going to pack the clusters 100,000 times better. 140. So it's almost 100, about 80 more layers were required to do the quick gen. But the quick gen is just another way where, maybe I just need to generate particles really quick because I'm trying to run a few test simulations to make sure my layer movements and geometry settings are correct. So again, not really any reason to use quick gen because the generation time is usually pretty insignificant compared to any simulation time that you use. Force time. What this does is these bottom three sections are really for very only special applications, and personally I've actually never even used them. So the force time says we're going to force Newton to drop a layer every 0.1 seconds. So this means that this tonnage above, that means nothing now, because rather than allowing Newton to determine how often to drop layers, we're forcing Newton to drop 1 layer every 0.1 second. So if I go and look at my output grid, birth time of layer 1, 0, 0.1, 0.2, 0.3, and so on. So now my tonnage is no longer going to be a constant 1,000 tons per hour. It's going to be whatever this would happen to be by forcing Newton to drop this layer. So you would never ever use this. I'm sure we stuck this in there for one particular client or one particular project, but in general you don't need to use that. Force count says let's force a maximum of 100 clusters in each layer and then go to the next layer. Or at least it should. Force count. Let's hover over this and see what it says. Specifies the max number of clusters that can be generated when quick gen is enabled. Oh, so do we have to enable quick gen to do this? There we go. So now it says each layer is going to have 100 clusters, 100 clusters, 100 clusters, and so on. And again, the point here is if for some reason you wanted to limit the number of clusters in each layer, you could do that. So it's tied to that quick gen, but no, not really any point in using that. The overlap, that says that by default when I generate material, if there is some sort of overlap in my layers, so if I go like this, so we've got overlap here, and by default each time Newton drops a layer, it looks and says, oh, are there any clusters that are going to overlap when I drop this layer? Are there clusters from the previous layer that are going to overlap and cause, crazy velocities and other unrealistic stuff to happen. If there is, then let's go ahead and delete those offending clusters so that they don't disturb the rest of the simulation. Now if I change this value, if I change this from, what was its default value? Oh, I don't remember if the default was yes or no. But if I change this, I will say, nope, don't delete those clusters and allow me to have this crazy screwed up velocity if I have layer overlap. And again, there's only very special circumstances when you might want to use that. So really, for the average user, looking at all of these advanced options, you might want to switch your pattern distribution to linear X or linear Y. And you might want to, speed up that increment multiplier. Or you might want to change the particle count so that rather than generating the default 10,000 before we copy, it'll generate 5,000 or 20 or 100,000. But other than those three options, you're probably never going to use any of the rest of these, and they're mostly irrelevant. So I think that covers these advanced options. And if you have any other specific questions about some of these, you can hover over the tooltip here and it'll read through what it does. Or you can send us an email and ask us a question about it. We'd be happy to answer. So, thank you.